In this video, I'll present our work on robust cross-modal representation learning with progressive self-distillation. Approaches to current vision language pre-training, such as clip and align, learn a joint embedding space by bringing corresponding image-text representations together while repelling unpaired instances away from each other. However, these methods remain data and compute inefficient, with much of their success attributed to a voracious appetite for billions of image-text pairs. This inefficiency arises for several reasons. First, the alt-text captions for web-harvested images can be noisy and inaccurate descriptions of the image content. Second, there exists many-to-many correspondences in a mini-batch, and the likelihood of observing negatives with high semantic similarity increases with batch size, which can further degrade the learned representations of shared semantics. To address this challenge, we propose to model these noisy, many-to-many relationships more accurately using soft probabilities rather than hard one-to-one pairings. This enables our method to simultaneously recalibrate potentially poorly matched or poorly annotated instances. Our approach is inspired by knowledge distillation, which utilizes a teacher network to provide soft targets to a student network. Conventional knowledge distillation offers numerous potential choices of teacher, for example, larger pre-trained but static networks, or networks that share the same architecture but use weights from a previous epoch or from an exponential moving average. The primary drawback to these approaches is the reduced computational and memory efficiency, as they require a secondary forward pass using weights that must be kept in memory. To circumvent these issues, we introduce a novel self-distillation strategy in the cross-modal setting, where the student network acts as its own teacher by estimating the soft alignment scores using the current state of the model. Since our objective relies on some basic alignment between corresponding image and text representations, we introduce a procedure that progressively increases the contribution of the self-distillation loss over the course of training. Our model therefore dynamically evolves into its own teacher. In the standard clip setting, the similarities between batches of image and text representations embedded by the respective encoders are supervised by hard alignment targets, enforcing a strict one-to-one alignment between corresponding image-text pairs. In contrast, we realize our self-distillation approach by first splitting a mini-batch into teacher and student partitions above and below the dotted line. The hard alignment targets above serve as teacher targets to supervise the teacher logits using the standard InfoNCE laws. In order to supervise the student logits, we employ a swapped prediction strategy that uses the corresponding teacher logits from the opposing modality as targets. By normalizing these predictions, the teacher provides the student with a distribution of soft alignment targets as desired. Over the course of training, the proportion of soft alignments provided to the student, as determined by a scheduled parameter alpha, increases as the teacher's representations become more reliable. This strategy stabilizes and accelerates training progress, allowing the student to reach higher levels of final downstream performance. We evaluate our method's zero-shot image classification performance on a host of benchmark datasets and compare it to its clip counterpart trained under identical settings. Given a fixed amount of pre-training data, our method consistently outperforms its clip counterpart over all 10 datasets, achieving as much as 6.19% absolute improvement in the CC3M pre-training regime. Plotting the average top 1 performance as the number of CC12M pre-training examples ranges from 600,000 to 12 million reveals that our method consistently learns representations more amenable to zero-shot classification for the same amount of data, and even suggests our gains may scale with pre-training size. To evaluate the effective robustness of our approach, we plot ImageNet accuracy on the x-axis and mean accuracy of ImageNet A, O, R, and V2 on the y-axis. Now, previous work has found that the in-distribution and out-of-distribution accuracies of ImageNet models follow a predictable linear trend, plotted in green, and CLIP models, plotted in red, establish a trend of improved effective robustness. We found that the slope of linear fit to our model is higher than that of CLIP, suggesting that our effective robustness improves over CLIP with increasing scale. Finally, we visualized the top 10 retrieved images for the text query, a cat lying on top of a chair in the living room, which suggests that our learned features more comprehensively capture all potential similarities between a text snippet and an image. For example, CLIP strongly targets the living room, but misses the cat altogether, while our approach captures all key aspects of the query, including cat, chair, and the living room. To summarize, this work presents a simple and effective contrastive learning framework that uses progressive self-distillation and soft image-text alignments to improve the efficiency and robustness of clip-like models without incurring extra computational costs. The simplicity of our approach allows it to be readily incorporated into existing and future methods. Natural future work includes scaling to even larger pre-training datasets with additional modalities such as audio and video.